So this is simple harmonic motion lecture number 3. In the previous classes, we have seen the different type of simple harmonic motion. We have seen the equation of simple harmonic motion. We have seen the equation of energy of simple harmonic motion. We have seen that there are two types of energy. One is potential energy and the other one is kinetic energy. We have seen the formula of potential energy and kinetic energy, both in terms of time and also in terms of x. Do we remember that? What we had gone in the previous class? The equation of kinetic energy and potential energy. Do we remember it? Okay. Now that takes us to the next topic. And in the next topic, what we are going to do is understand SHM by an example. And the simplest example for a body performing SHM is given by when a body is attached to a spring. Do we remember spring? If a body is attached to a spring, you can compress it. The spring will get compressed, but again it will come back to its original position. If you extend the spring will pull you and it will try to bring the particle back to its original position. There are two types of spring that you might see. One is the helical spring, which is the spring that we will be using. One is the spiral spring, which hardly we use, so we will not get any question based on that. This is just for your knowledge that these two springs are given. There is nothing that we need to understand here in terms of spiral springs, because spiral springs we will not be solving any question. It is out of your course. What we are going to solve questions on will be based on your helical spring, your normal spring that we have used, the helical spring that used to be in your ball pen. That is the spring that we will be encountering, and whenever we encounter such a helical spring, if you compress or stretch the spring by giving it a small displacement, the spring will try to come back to its original position. If you compress the spring will push the block if there's a block attached to it. If you extend the spring will start to pull the block back, and the force with which the spring pulls the block, we have found out that it is proportional to negative of the displacement. Negative sign indicates that if the displacement is towards right, force is towards left. If the displacement is towards left, force is towards right, or I can write force is equal to minus kx. Now this same formula we had derived for SHM. Same formula has come here. That means the system of spring attached to a spring is nothing but it will perform SHM. Here K is known as spring constant. There we had called it as force constant. Here we are calling it as spring constant. We must remember that the spring is considered to be massless. So the force in the spring is same everywhere. If the spring is not massless, the force at different points will be different, and the formula will be different. I'll tell you the formula for mass wala spring as well. You can note it down. But before going here, remember that the constant K depends on length, radius, and material of the wire. And this is a very important relation, that this K is inversely proportional to length. So if I cut a spring into two halves, I make the length L by 2. If I cut the spring into two halves, I make the length L by 2. The spring constant will become 2 times. Do we understand this? Can I have some raise hand that we understand this? So I'll give you a minute to note down these 3 points, and I'll come back after that. 1 minute. Let us move forward, and here we will see what happens when a spring is stretched. When the spring is stretched, the spring will apply a force in such a way that the spring comes back to its original position. When the spring is compressed, again the spring will apply force in the opposite direction to come back to its original position. Now there is work done to bring the spring. There is a work done when the spring is stretched by an amount x. This work done is the energy stored in the spring, which is half k square. This energy is coming similar to what we had seen in SHM, the energy of the potential energy in SHM. Here, remember, the potential energy of this SHM is stored in spring. And as you can see, the graph between potential energy and x is a parabola. Remember, the value of x is a sine omega t. If I stretch the spring from 1 to 2, L1 to L2, in position L1, the potential energy will be half kx L2 square. In position L1, it will be half kx L1 square. In position L2, it will be half kx L2 square. You can find out the work done as final energy minus initial energy. This is how you can find out how much work has been done to stretch the spring from L1 to L2. Do we understand this? Half k x1 square or half k L1 square is the energy stored in the position L1 or x1. Half k x2 square or half k L2 square is the energy stored in the position L2. Subtracting these, we will get the value of how much work is done to stretch the spring. I'll give you a minute to note this down. Note down the parabola again. Note down the equation of potential energy again. Remember, this potential energy is stored in the spring. I'll give you a minute to note it down. Let us move forward and see some important points. Remember, these important points will come as questions in your exam, and this is how questions are framed. Now, remember, if we have two springs of spring constant K1 and K2, K1 is more than K2. If they are stretched by the same amount, that means their displacements, their stretching amount is similar, then the work done will be, in first case, half k x1, half k1 x1 square. In second case, half k2 x2 square. X1 and x2 are same, but k1 is more than k2. In that case, work done in the first case on the first spring will be more than work done on the second spring. If they are stretched by the same force, remember, in first case, they were stretched by the same amount. In second case, they are stretched by the same force. Again, the ratio of work, half k1 x1 square divided by half k2 x2 square, but f1 and f2 are same. K1 x1 is same as k2 x2. So x1 by x2 becomes k2 by k1. In that case, what w1 by w2, work done in first case divided by work done in second case, will be k2 by k1. Remember, in the first case, it was k1 by k2. In such a case, work done in the first case will be less than work done in the second case. I hope you understand the difference between the two. In first case, W1 by W2 was coming as K1 by K2. In second case, W1 by W2 was coming as K2 by K1. Remember this point. The same point will come in exam. I'll give you a minute to note down this in your sheets as well as in your notebooks. Please note it down. Let us move ahead and see the next heading. Next heading is spring pendulum. What is a spring pendulum? Whenever a small mass is suspended from a massless spring, remember we always consider spring as massless, then this arrangement is known as a spring pendulum. So basically you hang a mass from a spring and that is spring pendulum. If the displacement is very small, so that spring does not get stretched along by a long amount, the motion is simple harmonic. Do we know this? Yes or no?
Yes, sir.
Yes, sir. I hope you know this. So now let us go into the diagram and see the formula for this. What is a spring pendulum and how it looks like. No surprises here because the spring pendulum looks like exactly what I had mentioned. A spring or spring constant K. Remember, this is a massless spring. A body of mass m is attached. Force will be equal to minus kx. So this k will become equal to m omega square x. Omega square will become k by m. So omega will become root over k by m. Frequency will become 1 by 2 pi root over k by m, and time period will become 2 pi root over m by k. Do we understand this? This is again very same formula, similar formula to what we had done in SHM. The only difference is we were calling F, we were calling K as force constant there. Here right now we are calling K as spring constant. So please mark these formula and I'll give you a minute to do it. It's better if you can remember these points and note down some special cases as well. So here are these cases. Time period of a spring pendulum is independent of acceleration due to gravity. It is 2 pi root over m by k. M is coming, k is coming, but acceleration due to a gravity, it is not coming. Therefore, a clock based on oscillation of spring pendulum will keep proper time everywhere on a hill, moon, satellite, or any place, any different planet, sun, moon, any star. Spring pendulum wala clock will always keep correct time because it does not depend on the value of g. If you increase the mass, time period is directly proportional to root over mass, so the time period will increase. But if you increase the force constant, the time period will decrease. Now, even if you hang a block like this on an inclined plane, or you keep a block like this on a horizontal plane, in both the cases, remember the value of omega square will be k by m. So it does not depend on how you have kept the block, whether you have hung it vertically or you have kept it horizontally or you have kept it on an inclined plane. In all the three cases, four cases, any number of cases, the value of omega square will always be k by m. Do we understand this? Do we understand this? Can I have some raised hand that we understand this?
Yes, sir.
The only thing that will be different in all the three cases will be the position of equilibrium that we will discuss in the next slide. I'll give you a minute to note down these points first, and I'll be back in a minute. Well, as I said, that in all the cases, whether you keep the block vertically hanging or inclined plane or on a horizontal plane, the value of omega, time period, and frequency remains same, but there is one thing that is different, and that is the equilibrium position. And now we will see the equilibrium position of all the three cases. You will mark them down. One case is there, the other two cases are not there. So you will mark them down. This is a vertically loaded spring pendulum. So the block is loaded vertically. In this case, when it is in equilibrium, the upward force is kx and the downward force is mg. So the equilibrium position x, or x naught I call it, that will be equal to mg by k. Do we understand this?
Yes,
Do we
sir.
understand this? Please raise your hands and let me know. This is a very important point because this question will come. So we can write here from this equation that mg by k will be x naught, the equilibrium position divided by g. So I can also write time period in this form, 2 pi root over x by g. But remember, the formula of g, the value of g is coming here, but remember that time period is independent of acceleration due to gravity. We have made a formula from the case given here, but remember, just because looking at this formula tells you that g is there, that does not mean that 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 time period depends on g. It does not depend on g. It is directly proportional to root over m. It is inversely proportional to root over k. Do we understand this? I'll give you a minute to note this down. Let's move ahead and write the other two cases and write the equilibrium position in the other two cases as well. The first case is when a block is kept on a horizontal surface when the block is kept on a horizontal surface. In this case, the equilibrium position happens when the value of x naught or extension is 0. That means the spring length is in its natural state. When there is no compression or no expansion, then we have equilibrium position in the case of block kept on a horizontal surface. This case is different from this case where the equilibrium position happens where kx is equal to mg. Do we understand this? Now look at the case where the block was kept on an inclined plane of angle theta. The block of mass m was kept on an inclined plane of angle theta. In this case, the equilibrium position happens where k into x naught is equal to mg multiplied by sine theta. Remember, mg multiplied by sine theta. So the value of x naught in this case becomes mg sine theta divided by k. Will you remember this? Now remember, this formula becomes a general formula for any spring. When the spring is vertical, the value of sine theta, the value of theta is 90. Mg sine 90 becomes mg. When the spring is kept horizontal, the value of theta becomes 0. Mg sine 0 becomes 0. Do we understand what I'm saying here? In this case, the value of theta is 0. And in this case, the value of theta is 90. Do we understand this? If you understand this, please raise your hands. When the block is vertical, the value of theta is 90. Sine of 90 is 1. Therefore, the answer is mg by k. In case of horizontal spring, the value of theta is 0. Therefore, the answer is 0. I'll give you a minute to note it down. Well done. Let us move forward. Again, an important case. If two particles are attached with a spring in which only one of them is oscillating. One, as you can see the case here, which I am going to show. As you can see the case here, this particle is kept on ground. This is not oscillating. Only this particle which is hanging in air is oscillating. Do we understand this? In that case, the time period will be equal to 2 pi root over mass of the oscillating particle. In this case, it is m1. So it is time period is 2 pi root over m1 by k. Omega square will be k by m1. We have to use the mass of the oscillating particle. Do you understand this?
Yes, sir.
You might have a case where both the particles are oscillating, especially this case. Please remember this case where both the particles are oscillating. So I kept the block M1 here. I keep the block M2 here. And then these both are oscillating. Now in that case, and remember this formula in which both are oscillating, the time period becomes 2 pi root over M1, M2 divided by m1 plus m2 multiplied by k. So basically in this case what happens, your mass m gets replaced by m1 m2 divided by m1 plus m2. So if both are oscillating, you put m1 m2 upon m1 plus m2. If only one is oscillating, you just put the mass of the oscillating body. Do we understand this?
Yes, sir.
I'll give you a minute to note it down. Well, then we come on to a special case where mass of the spring is given. So remember this case, mass of the spring is also given. And we say that let us say that the mass of the spring is ms. In that case, what we do, omega square becomes k divided by whatever mass is there plus ms by 3. This is a very important formula that you must remember. This implies your time period will become 2 pi root over m, which is the mass of the block, plus ms by 3 divided by k. Can you remember this formula for me, bacha? I'll give you a minute to note it down. I'm giving you all the formulae. Any one of these formula will come in the exam. Okay, then the next heading that you will write is the combination of springs. Combination of spring. The first combination is known as series combination, in which you can see both springs attached like this. This type of combination is known as series combination. Do you know this? Yes or no? Please let me know. Do we know this series combination? Have you seen a series combination of spring? This is same as series combination of two resistances. When two resistances are kept one after the other, it is known as series combination. Do we remember this? Please let me know. Yes or no?
Yes, sir.
Whether they are kept in the horizontal position or in this case they are kept in the vertical position. In both the cases, this is series combination of springs. Do we understand this? Yes or no? Do we understand this? Yes or no?
Yes, sir.
Yes, sir. Then there are two things that you must remember here. There are two things that you must remember and you must mark it very correctly. In this case, what is going to happen when you have series combination of springs? Force acting on both the springs is equal. Both the springs will have equal forces. In first case, the force is minus k1x1. In second case, the force is minus kx2. Both the forces are equal. Very important point. But displacements are different. Displacements are different. Forces are equal. Total displacement is given by this formula. Remember that. What you got to remember? What you got to remember in series combination? Point number one, force is equal. Point number two, displacements are different. Total displacement x is x1 plus x2. Can you remember this for me? And note down these points which I've highlighted. Yes or no? No or yes? Yes or no? No or yes? I'll give you a minute to note it down. Let us proceed and see what happens next. As we have seen what happens in series combination of resistors, current is same but potential difference are different. We can replace the two resistors by a single resistor. Here, we can replace the two springs, or if there are three springs, or if there are four springs by one single spring. And how do I get the value of that effective spring constant? 1 by k effective will be 1 by k1 plus 1 by k2 plus 1 by k3 and so on. Do we remember this? Yes or no? If there are only two springs, the effective spring constant becomes k1 k2 upon k1 plus k2. Time period becomes 2 pi root over m by k effective. You just put the value of k effective k1 k2 upon k1 plus k2. For frequency, it becomes 1 by 2 pi root over k effective by m. Angular frequency omega becomes root over k effective by m. Do we understand this? Can I have some reason that we understand this? What happens in series spring? If the springs are in series, forces are same, displacements are equal. We can replace the springs by a single spring. I'll give you a minute. It's a very important formula that you will have to note down. Okay, then let's move ahead, and these are the points again written in words for your understanding. In series combination, same force exerts, but extensions will be different. In series combination, extension of spring will be reciprocal of its spring constant because forces are same, F is equal to kx. So extension will be reciprocal of the spring constant. Spring constant is reciprocal of the length. If you remember all these things, k1 x1, extension will be equal to k2 x2. So x1 by x2 will become k2 by k1. The spring which has less force constant will extend more. The spring which has more spring constant will extend less. Do we understand this?
Yes, sir.
I'll give you a minute to note it down. Fatafat, move fast. Well done, sir. Since we have done a series combination of springs, now we will move on to the parallel combination of springs. Any combination like this, you might say, sir, this looks like a series combination. No, it is not a series combination. This is a parallel combination. This is also example of a parallel combination, and this is also example of a parallel combination. What is going to happen here if I move this by x here, if I move this by x here, if I move this by x here, both the springs will have same displacement. X will be same, force will be different. Do we understand this? What has changed? In first case, in series combination, forces were same, X were different. Here, X is same and force is different. Do we understand this? Yes or no? No or yes? Do we understand this? Yes or no? No or yes? So what will happen here is total force will now become F1 plus F2. Very important point. Total force will become F1 plus F2, but the displacement will be same. In this case, what we can do is we can replace the two springs by a single spring, and the force constant of that single spring will be K1 plus K2 plus K3 plus K4 and so on. If there are only two springs, it will be K1 plus K2. Time period will become 2 pi root over m by Kp. Kp means effective spring constant in parallel combination. Kp here becomes K1 plus K2. So you just remember K, you just replace K by K1 plus K2 and you get your answers. What are the important things that you must remember? Here you must remember that X is same. Do we see this?
Yes, sir.
Force is different. Total force is F1 plus F2. We have just reversed the previous case and I'll give you a minute to note it down. Okay, then we'll just go through the points once again. We noted down the formula for time period. This is the formula for frequency, and this is the formula for angular frequency. Parallel combination, different forces exert, but the extension will be same. In parallel combination, force on the spring will be proportional to the spring constant. X is same, forces are different. Forces are proportional to spring constant. In the previous case, X was different, forces were same, and X was inversely proportional to the force constant. So you can remember this. Any one of this will come as questions in your exam. I'll give you a minute to note it down. Well done, sir. Then comes a question, sir, and the question is right on your screen, sir. Can you tell me the answer for this one? And I'm waiting for your answers. In the adjoining figure, the frequency, remember they are talking about frequency. The frequency of oscillation of the mass will be proportional to which one? What type of combination is this, my dear bacha? No idea? Are they in series or are they in parallel?
Parallel.
They are in parallel, so the frequency of oscillation will be proportional to what? Please let me know, beta. I will be very disappointed if you can't tell me the answer. Frequency is 2 pi by omega, so it will be omega square is k by m. So it will be proportional to 1 by k1 plus k2 ka root. Do we understand this?
Yes, sir.
And I was disappointed that you cannot give me the answer. That's a disappointing thing. Very disappointed. I hope you can give me the answer for this one. As shown in the figure, two light spring of force constant K1 and K2 oscillate with a block of mass M. What will be the effective force constant? Can you tell me the answer for this one? Bacha. What is the effective spring constant in this case? Can I have the answer, bacha? And the option is D, K1, K2 upon K1 plus K2. Do we understand this? Do we understand this, beta? This was a combination of series. Do we understand this? Yes or no? Okay, the mic has gone. Okay. Move on to the next one. Can I have the answer for this one? You can tell me by your fingers. 1, 2, 3, 4. It's a very straightforward and very simple question. They've asked you the time period. Can I have your answers, please? I'll give you a minute. Can I have your answers, please, beta? What is the time period of the system? A, B, C, D. What is the answer? Yes, the answer is definitely 4. Well done. You have cracked this question. That is great. Last one on this. Last one on this. What about this one? The total spring constant in this case. Remember, this is a combination of 3 springs, but 3 springs are put in a different way. How will you do this? I'll give you a minute to think about it. A minute. So, do we have the answer? Yes, yes. That is great. I was not expecting. That is great. Remember, these 2 springs, which 2 springs? The upper wala 2 springs K1 are in parallel, so their effective spring constant becomes 2K1. Then it is in series with K2. So the effective spring constant 1 by K will be 1 by 2K plus 1 by K. So K will be the ulta of this. 1 by 2K plus 1 by K2 ka inverse. Well done, bacha. I'm really good. I'm really happy that you have understood this concept of effective spring constant. Now the last thing that remains in this particular chapter is time period of a simple pendulum, and we'll just go through the formula. You will draw the diagram, write the heading, and we shall move away. Do we understand that this is a simple pendulum? It is attached to the ceiling at this point. M is the mass of the block. You don't have to go into the details of this. You must only remember that K will be equal to mg by L. In this case, time period will be equal to 2 pi root over m by k. The formula becomes 2 pi root over L by G. Here omega square becomes G by L. These are the 3 formulas together with this diagram that you must remember. And remember that the angle of oscillation must be small for the motion to be SHM. They can ask you as a theoretical question, what will happen if the angle is more? Is it simple harmonic? Then you will say no. If the angle is high, if the angle is more, then the motion is not simple harmonic. Do we understand this? Can I have some raise hand from all of you guys there? I'll give you a minute to note it down. Okay. So we have seen that the time period of a pendulum is equal to 2 pi root over L by G. From here, we can find out or write 2 things. Number 1, time period is directly proportional to root over L. If I make the length 2 times, time period will become root 2 times. Number 2, time period is inversely proportional to the value of acceleration due to gravity. So, time period of a simple pendulum depends on acceleration due to gravity, but time period of a spring pendulum does not depend on acceleration due to gravity. If you take simple pendulum on moon, the acceleration due to gravity is 1 by 6 times. and therefore the time period will become root of 6 times. Do we understand this? Yes or no? I'll give you a minute to note it down. Well, then let's move ahead and see some cases which might come as cases in your exam. What I have done here, that I have a simple pendulum of length L, mass m, but it is kept. It also has a positive charge, and the pendulum is placed in a uniform electric field which is pointing downwards. Now, if this happens, what will happen? Apart from gravity, which is acting downwards, a force QE will also act downwards on this charge, and then I can write the time period as t pi 2 pi root over g plus QE by m. Remember, this g plus QE by m basically does the calm of g effective. Basically, g has become more. How much more it has become? QE by m, because the force was acting downwards. If in place of this charge being positive, if this charge was negative, minus q, then the force would have acted upwards, and in that case the value of g would have become minus QE by m. So you just replace g by g effective. In first case, blue case, you have replaced it by g plus QE by m. In second case, red case, you have replaced it by g minus q by m. Do we understand this? I'll give you a minute to note this down. Let us move ahead and see what would have happened if electric field was pointing upwards. In red case, the charge is plus q and the electric field is upwards. In this case, the value of G effective, because force is acting on the upward direction. In this case, G effective ka value becomes G minus QE by M. But if I had a negative charge, which I am showing it by the green thing, if I had this charge as minus Q, in that case, force would have been in downward direction. In that case, the value of G effective here would become G plus QE by M. Remember, a positive charge will experience force in the same direction, but a negative charge will experience force in the opposite direction. Do we understand this? Yes or no? Can I have some reasons? I'll give you a minute, 2 minutes. Well done. Then the next thing is something known as the seconds pendulum. What is the seconds pendulum? People, students get confused sometimes. They understand or they think that seconds pendulum is a simple pendulum whose time period is 1 second. 1 second. Remember, its time period is not 1 second, but its time period is 2 seconds. Now, if I put the value of time period as 2 seconds on Earth, the value of G is 9.8, and you can take it approximately equal to pi square. The length of a seconds pendulum on Earth will be approximately equal to 1 meter. So if I take or if I make a pendulum of 1 meter on Earth, it would give me a time period of approximately 2 seconds, and that will become a seconds pendulum. Do we understand this? Yes or no? No or yes? Well done. Well done. That takes us to the last part of this particular chapter, where we have a simple pendulum kept in a lift or in a difference reference system apart from Earth. Here the lift is going up with a velocity v. It could have come down with a velocity v as well. Remember, wherever you have different values of g or different values of g effective, the time period becomes 2 pi root over g effective. We have already seen that in the question of charge and electric field. Yes or no? No or yes? Here also we will replace g by g effective, but here acceleration is 0. The lift is moving with a constant velocity. Therefore, the value of g effective remains g. Therefore, the time period in this case, when the lift is moving up or down with constant velocity, the time period remains same, t pi 2 pi root over L by G. Do we understand this? Draw the diagram, write the formula. I'll give you a minute. Well, that takes us to the next case where the lift is moving upwards with an acceleration F, or you can say acceleration A. If the lift is moving upwards and we are in a upwards accelerating frame, we will put a force in the downward direction. A pseudo force will come in the downward direction, and therefore the time period becomes T is equal to 2 pi root over L upon G plus F. The time period decreases when the lift is moving up with an acceleration A or acceleration F. The effective G becomes G plus A or G plus F, and the time period decreases. Have we noted it down? Do we understand this? Yes or no? Please note this down. I'll give you a minute. Well, let us move ahead and go on to the last part of this particular chapter. And in this last part, the lift will be moving down with a constant acceleration F. In that case, we'll have to apply a pseudo force in the upward direction, and therefore the effective value of G becomes G minus F. The time period increases if the lift is falling down freely, the cord has broken and the lift is falling down freely, the effective value of G becomes 0. Time period becomes infinite and the simple pendulum will not oscillate. Do we understand this? Please note it down. I give you a minute to do it. That takes us to the next case. In this case, instead of lift moving up and down, it is kept in a truck which is moving in a horizontal plane on a horizontal road. If the simple pendulum is mounted on a truck which is moving like this on a horizontal plane, if the truck is moving with a constant velocity, no pseudo force acts, and the formula remains T is equal to 2 pi root over L by G. It does not change. Do we understand this? Yes or no? No or yes? I'll give you a minute to note it down. I hope you have noted it down, beta. And we move on to the next case where the truck is accelerating towards right with an acceleration F. In that case, the value of G effective, remember very important formula, becomes root over G square plus F square, and the time period starts to look a bit more complicated. T is equal to 2 pi root over L divided by root over G square plus F square. Remember, the vertical angle with the equilibrium angle here also changes, and remember that tan of this equilibrium angle is F, the acceleration, divided by G. If the truck was moving on the right hand side, the condition would have come on this side of the motion. Do we understand this? If the truck is moving forward, the simple pendulum will go this way. If the truck is moving backwards, simple pendulum will move this way. Do we understand this? Yes or no? I'll give you a minute to note it down. Well, with this, we have come to the end of this chapter of simple harmonic motion. We have seen all types of cases. To give you a short recap, we have seen the equation of motion of simple harmonic motion. When is the motion simple harmonic motion? We have seen the equation of potential energy. We have seen the equation of kinetic energy. We have seen what is a spring pendulum. We have seen the omega for spring pendulum. For spring pendulum, what all factor it depends on. We are done with this chapter. What I'll do is I'll give you time, 5 minutes, to go through this entire chapter. If there's any doubt, I can clear it now. And then we will move on to the next lecture. We'll start with wave motion. So I'll give you 5 minutes. I'll be back and we will start with wave motion. Take care. 5 minutes we have got. Steady.